guys, so this is the lecture video for 8.8. This is our last section in the semester, so be proud of yourself because we've gotten this far, and we're actually ending on a pretty easy note. So this is vectors. All right guys, so let's talk about what a vector is. It looks like an array because it starts with a point and it has an arrow at the end. But it's not an array, it's actually just a line segment. So this arrow is a little bit misleading because when we see the arrow, we think, oh, well, that goes on forever in that particular direction. But a vector actually has two endpoints. So you can think about this as an endpoint and an arrow. So it's really what we like to call a directed line segment. The arrow needs to be there because we need to know the direction that the vector is going. So the arrow is just to show direction, not to show that it is going on forever. Vectors have what we call an initial point and a terminal point. And we use these 2 points to determine some things about the vector. So with an initial point and a terminal point, notice we could talk about the distance between those 2 points. You guys, that distance between the points, really distance, is what we call the magnitude of the vector. And you guys, the magnitude of the vector, so it explains how much of a particular force that's being acted upon. So for example, if you've ever watched like a meteorology weather report, you see the wind speeds and stuff on a map, and you might have like, bear with me, this is a map of Oklahoma. Oh, that's good. That's a good one, guys. So let's say this is Oklahoma. I don't know why, hold on, I gotta fix it. Looks more like that. Anyway, so we got a map of Oklahoma and you're looking at the wind speeds. And there's a bunch of different arrows going all over the place. And maybe some are like this, and some maybe are really long, and some are really short. And they're all over the place. It's usually not exactly like this. That's some very variable winds. But anyway, those arrows talking about wind speed explain not only the direction the wind is going. So you see these arrows all pointing up northeast. You can say, okay, so the wind is moving northeast, but the size of these little vectors are telling you how fast the wind is moving. So like these two large vectors pointing southwest, they're larger, which means the speed of the wind going that way is faster. So in this example, our vectors are explaining the direction of the wind and the speed of the wind. So the magnitude, the length of the vector, is the speed in this case, but it's not always speed. You can explain a lot of different forces using vectors. You could have a heat field vector, and the magnitude could be the amount of heat and the direction it's going. So a lot of different examples can be explained with vectors, but basically anything that has both a direction and a force attached to it. So the distance between the 2 points, how long that vector is, does tell us the magnitude, and we'll talk about how to find that. And then obviously the arrow tells us the direction that force is going in. Okay, so this is what a vector is. Let's look at an example of how we can find information about a specific vector. So the first thing we're going to find is what we call the component form of a vector. So I'm going to give you an example of a vector. Now, this is in space, so this particular direction might not be super accurate, but actually it's not accurate at all, because one thing that we can find about a vector is the location of its initial and its terminal points. So my arrow is a little off, it should be a little up more, but that's okay. because we're given the location of a vector with ordered pairs. So let's say this is somewhere in the plane. I want to know the component form of the vector. All right, so first I'm going to give this vector a letter name, and usually for our vectors they just have a single letter name. You'll notice that when you see these letter names in your homework that they're bold, and that notates to us that this is a vector. Now, when I'm doing problems on the board, I can't make some of my letters bolder than other letters. So if you're handwriting, then I'm going to call this vector U. And instead of just making it extra bold, which is hard when you're handwriting and not typing, another way to notate that I'm talking about a vector is to put a little arrow on top, or a little half arrow. So you're going to see me do the little half arrow to talk about a vector name, but in your homework it's just going to be a bold letter. So I want to talk about the component form of the vector U. So the component form of a vector actually looks like another ordered pair, but it's not an ordered pair. It talks about the left-right component and the up and down component of the vector. So these are what we call components. So we have a horizontal component and a vertical component. Let's say that, let's use A and B. So you guys notice the pointy brackets? So that's something that tells us we're talking about components of a vector and not just ordered pairs with parentheses. But if I want to find the components A and B of any vector, it's actually really easy. I just use my terminal and my initial points and I subtract. So to find the component form of our vector U, to find the horizontal component, think about x values here. It's going to be x minus x. So I'm going to have 2 minus 0. To find the up and down movement, that's the y value, right? So 4 minus 0 in this case. And you guys, we get our two components, 2, 4. Now, notice on this vector, our component form, 2, 4, these are the same values as your terminal point, 2, 4. That doesn't always happen. The reason it happened on this question is because we started at 0, 0. Think about it. If these had been other numbers other than 0, when we subtracted, we would have gotten a different value than 2, 4. But on this easy example, we get this 2, 4. So let's do another one. Let's say I have a vector whose initial point is 3, 5, and its terminal point is -2, 8. So again, not super to scale because, well, you know me. But anyway, so we have initial and terminal. You guys, they're not always labeled, but if you're looking at a picture, you know the terminal point's the one with the little arrow on it. So I want to know the components of this vector. Let's call this vector V. So V equals some pair of AB components, A being the difference in X values, or the horizontal component, and B being the vertical, or the difference in Y's. So for A, always terminal minus initial. I know it was easy to see in the first example, but I've got this one a little backwards. So start with your terminal minus your initial. You guys, let's do -2 minus 3. And 8 minus 5. -2 minus 3 is -5. 8 minus 5 is 3. So we get our component form of this vector, -5, 3. Now, what is cool about knowing the components of a vector? Well, one thing that's cool about it is that we can graph a vector. So this vector, I did have points, but I didn't necessarily put it in a plane. I guess I could have, but I just kind of left it out in space. When you have the component form of a vector, it's really easy to graph in the plane because what you do is you actually use these like an ordered pair. So -5, 3 are the components of this vector. When we graph vectors in the plane, we always start from the origin and then we go to those components. So the horizontal component is -5, the vertical component is 3. So it would end here. You know where it starts. It always starts from the origin. And we get this vector here. This is the vector v, but what the component form does is it sticks it in the plane starting at the origin. Notice if I had graphed this in the plane, I totally could have because I had ordered pairs, but it wouldn't have started at the origin. It would have started up here at 3, 5 and ended here at -2, 8. I want you to see the similarities between these two vectors. They're exactly the same length and exactly the same direction. What's the difference? Well, the difference is I put it in component form so I could make the vector start at the origin, because it's really helpful for us if we can look at a vector and do calculations on it when it starts from the origin. So, yes, exact same vector, but I started it in a different place by finding the components of the vector. So you have some questions that will give you an initial point and a terminal point of vectors, and you just subtract the x's and y's and give the component form. You guys, having a vector in component form is really great because it's easier to find the magnitude of the vector in that case. So I had mentioned the magnitude being the length of the vector or the distance between the 2 points, and it explains what kind of or how much of a force is acting upon that vector. But the easiest way to find the magnitude is if you have your vector in component form. So let me give you a vector in component form, and we'll talk about finding the magnitude. I want to start with a generalization. So let's say we have a vector starting at the origin. Maybe it looks like this. Initial point, terminal point, let's call this u as a vector. Let's say that the terminal point is at A, B. This vector, because it starts at the origin, is in component form. So if you took the initial point at the origin and the terminal point that I'm calling AB, and you did the subtraction, what would you find for the component form of u? Well, it's pretty clear. It's like that first example. Because it already started at the origin, the components are actually just A and B. And you can do the subtraction A minus 0, B minus 0 to find it. But here's the components. Now, I've got this vector sitting here, and I want to know the distance between these 2 points. And you guys, we have done this so many times in different forms. But let's do it again. We drop down the line. We see the right triangle. I know that the distance across here is A. And I know that the distance up and down is B. What's the distance or the magnitude that I'm looking for? Well, I know that just like x, y, and r, or using the Pythagorean theorem, that the distance there, what I'm going to call the magnitude of u, sorry. So you guys, new notation. Magnitude, length of a vector, the distance between initial and terminal points. I can write it as the vector with kind of like absolute value signs on each side. The magnitude of u, the distance here the square root of, in this case, a squared plus b squared. So remember, if this was r and we had x and y, it'd be the square root of x squared plus y squared. Well, we're using a vector notation and we're using a and b now, but it's still pretty easy to follow that this looks just like the ones that we've done before, looking for a certain length. All right, so if I want the magnitude of any vector in that's starting at the origin in component form, you're just going to do the square root of a squared plus b squared. So let's do an example. Let me see, where's my example? Ah, there we go. See you guys, I've got a vector v, and it equals 6, negative 3. So because you see the pointy brackets, because there's only one pair of numbers here, you know it's already in component form. If you were to graph this, you would start at the origin, go over 6, 1, 2, 3, 4, 5, 6, and down 3. And the vector you were looking at would be right here. You don't have to graph this one. All you have to do is find the magnitude or the distance here, the length of v. So you guys, in component form, your first number is a, your second number is b. Just do the square root of a squared plus b squared. So the magnitude of b is the square root of 6 squared plus negative 3 squared. Careful when you square that negative, you know it's going to be positive. Well, you get the square root of 36 plus 9. That's the square root of 45. You guys, you're going to have a lot of square root answers. Just remember, keep them exact, but simplify your square root. So you guys, this square root does simplify to 3 root 5. So you'd call that 3 root 5. And that's the magnitude. That's the length of that vector. I did graph that vector right here, but remember, you don't have to. You just have to find the magnitude. Okay. So we can find the distance or the magnitude of a vector using its components. And you guys, you will only have to find magnitude when it's already in component form. So I don't even think there's any that you have to graph. So it'll give you questions that look just like this or just like this. And you just take these two numbers as a and b, and you do the square root of a squared plus b squared, and you've got your answer. Okay, so finding magnitude is something that's important to us with vectors. Now, I'm going to do a couple more things with vectors, and they're going to be operations that we can perform on more than one vector. So let's say we have two vectors u and v. Let's say that u is our AB components. I need to pick different letters for the components of v, so I'll just use C and D. But you've got two vectors in component form. What if I want to add them together? I want to do u plus v. You guys, it's really easy to add two vectors together. You take the two first terms and add them together, and then you take the two second terms and add them together. So in our general form, it would be a plus c for the first component and b plus d for the second component. So let's give this an actual example. Let's say that I have a vector u that's 2, negative 3, and I have a vector v that's negative 4, 5. I want to add these two vectors together. So u plus v. So the two first terms, I'm going to do 2 plus negative 4, or 2 minus 4. And then I'm going to do negative 3 plus 5. So I add them separately. I never mix A and B or C and D together. I leave it with the comma in between. So my first component is going to be negative 2. And my second component is going to be positive 2. So add the two firsts, add the two seconds. So really easy, yeah? And yeah, you would be right if you think that, because it's very straightforward. What if I want to do u minus v? How do you think that works? Well, it works the exact same way, except we'll subtract the two first terms and we'll subtract the two second terms. So you guys, let's find u minus v for this example here. So u minus v would be 2 minus negative 4 and negative 3 minus 5. So what we get there is, this is like 2 plus 4 now, so it would be 6 and then negative 8. So we have u plus v, u minus v. You will have vectors that you have to add and subtract from each other. The next operation that we can do with vectors, so we did addition and subtraction. You feel like the next step would be multiplication. And it kind of is. We're not ever going to multiply two vectors together, but we can take one vector and multiply it by a number. So let's talk about what we call scalar multiplication. So adding and subtracting was very straightforward, and this is actually pretty straightforward too. The word scalar might be new to you. The word scalar is just, it's another word for just a normal number. So, for example, u is a vector. I know it's a vector because it's noted as a vector. But if I add another variable in there, let's say k. Notice it's not a vector. I didn't notate that this stands for a vector. It just stands for itself. K is just a number or a scalar. So anything that says it's a vector, you can say, okay, that's a vector. It has components. K is just K. It's just a scalar. So I have my vector u. It's going to stay A, B components. And K is just a scalar, which just means it's any number. In your examples, it will actually be a number like 1, 2, 3, 4, 5. What I want to do is I want to take K and multiply it by my vector u. So I want to take my vector and multiply it just by a number. So let's see what that would look like writing u as components. So it's like taking your scalar, or just your number k, and multiplying it by the components of u. This works exactly how you think it should work. We are going to distribute. You're going to multiply this k by both a and b. So what we get for k times u is ka and kb. It really is that easy. Let's look at an example. So if I tell you that u is 3, 7, but I want you to find 2u. So notice 2 is a scalar. It's just a number. It's not representing a vector or anything else other than just being a 2. 2 times the vector u is 2 times the components 3, 7, and multiply each of those numbers by 2, and you'll get 6, 14. And there's 2u, and that couldn't be easier, right? This is kind of nice to have something easy. Okay, so we've got the scalar multiplication. Let's put it all together in an example. So you have some examples where you will both have to add and subtract vectors and multiply them by some number. You guys, order of operations is pretty much the same when you're doing all this stuff with vectors. If you have a scalar multiplication, you're going to do it before you do any adding or subtracting. So if I have two vectors, u equals -4, 8, and v equals 2, 5, I want to find 2u plus 4v. guys, the very first thing you're going to do is the scalar. You're going to find 2u and you're going to find 4v, and then you can add them together. So what is 2 times the vector u? Remember, it's just 2 times each of these components. I'll get -8, 16. There's 2u. So let's note, just to keep track of what we're doing, that's 2u plus, we need to find 4v. Well, 4v is just 4 times both of these components. So we'll get 8, 20. Now what do? Well, I add together. Remember, adding the a's and adding the b's. So I'll have -8 plus 8. So that leaves us with 0 for your horizontal component, or your a value. Positive 16 plus 20 is 36. So that's our answer. That is 2u plus 4v. We did the multiplication first, then we added. You guys, you could see these in multiple different combinations with plus, minus, different numbers here. But you should be able to use the order of operations, multiply, then add or subtract, to find any answer that you're looking for. We have one more operation to do with vectors. I said that there's no true vector multiplication. You can't take a vector, multiply it by another entire vector, and get a new vector. That's not something that happens, but we kind of have a form of that. We have what we call the dot product. So the dot product is an operation exclusive to vectors. It's really easy to find. It's a lot like multiplication with one certain difference. So we've got your vector u equals the AB, and v, let's call that CD again. And what I want to find is u dot v. So I'm emphasizing this dot, making it a little bigger than it really is. But it is not just a multiplication sign. So when you see a dot, you think, I'll just multiply. But when it's between vectors, it's not multiplication. It's called the dot product. So I want u dot v, and that's how I say it. I just say the word dot. This is how you find it. You do multiply your first two numbers. So I'm going to do a times c. And I'm also going to do b times d. So it seems like I am just multiplying the two vectors, the first terms, the second terms. Here's the big difference. There's not a comma in between. This doesn't turn into a new vector with new components. You multiply those two terms together and add them. So what does that mean? It means you have a number here and a number here. You add them together and you get a single number. So what's cool about the dot product is you start with two vectors, but what you end up with is a scalar, or just a normal number. So when you're doing a dot product, make sure you're not ending up with separate components. You should just get a single numbered answer. So let's look at an example. Let's say that u is, I'm just going to use this template I already have. Let's say that u is -5, 2, and v is 9, -8. I want to find the dot product. I want to find u dot v. So the first thing I'm going to do is -5 times 9. There's a plus in between. Then I'm going to have 2 times -8. So you do multiply them separately. Just make sure you do add the two values you get at the end. So this is -45 plus -16. Add them together and get -61. And there's our dot product. You guys, that's the end. This is the last topic that you'll learn in this class. I think it's nice that we're ending on such an easy note. But if you do have questions, remember come into the office hours and I can help you.